Okay, so here's what we're going to do. We're going to take a sphere of radius r. We're going to take a cone defined by z equals the square root of x squared plus y squared. And what we want to do is find the volume of this ice cream cone bounded by the cone on the bottom and the sphere on the top. Okay, that's what we want to do. All right? We're going to set this up 3 different ways. The intersection is going to be this circular region, and we have to find its equation. So, how do you find this equation? What we're going to do is take z, substitute it in here for z to get x squared plus y squared plus z squared, which would be x squared plus y squared, equals big R squared. We're going to have 2x squared plus 2y squared equals big R squared.
So you plugged the sphere of the cone into the sphere?
Yes, I did.
The cone into the equation of the sphere.
That's exactly what I did.
What did we find with that?
What we're finding is the intersection of these 2 objects. These 2 solids in space, these 2 surfaces in space, we found the intersection of these 2 by substituting that z value in for z here in the sphere. Okay? And then get x squared plus y squared is equal to r squared all over 2. Or r over the square root of 2 squared. Okay? In other words, this is a circle in the xy plane whose radius is r over the square root of 2. Okay? That's what this point would be right here. Okay, you with me on this? So, the equation of this circle, x squared plus y squared equals r squared over 2, has a radius of r over the square root of 2. That's this circle right here, the intersection, down at the xy plane. Okay? You with me so far?
Yeah.
Okay. All right, we're going to set up 3 different triple integrals. Okay? 1 in rectangular, 1 in cylindrical, and 1 in spherical to find the volume bounded by these 2. So let's do it. Are we all set with that so far? Yeah. All right. So, first, rectangular. That volume is going to be the triple integral of the top surface z, which is equal to r squared minus x squared minus y squared. That's our the top surface is the sphere, minus the bottom surface, dz, dy, dx.
Can you explain what the root things come from?
What I'm doing is solving for z in the sphere. This is the sphere solved for z. And when you solve for z in the sphere, subtract the x squared, subtract the y squared, and then take the square root. And that's what this is here.
We're solving for z.
Yep, this is what z is for the sphere, and this is what z is for the cone.
Okay.
That's exactly it. So you got top surface minus bottom surface, okay? It's not what I wanted to do. Okay? Sorry. This is not what I wanted to do. What I want to do here, we're just finding the volume. This is not correct. I'm sorry, it's not correct. Because here's what it is. We have to do, these are the limits of integration. Okay, if I were doing a double integral and finding the volume, that's what I would have. I would have top surface minus bottom surface with a double integral, and that would work. But a triple integral, it's the limits of integration, goes from bottom. The bottom surface will be the cone. Sorry. The top surface is that square root that I just had in here. Okay. Okay. If I were doing a density, had a density function, and we're finding the mass, we would put the density function in here. Okay? If I wanted to find the center of mass of that object, we would have a density function in here, and we'd have a distance here. Usually it's z, the distance from the xy plane. But all I'm doing is finding volume. So it's the triple integral, bottom surface to top, okay? Sorry. And the y values and the x limits will come from our region in the xy plane. Okay. And we said the equation of this is x squared plus y squared equals r squared over 2. Okay. That's the equation of that circle. So, I'm going to multiply by 4, and I'm going to take just this piece. Okay? All right, what will my y limits be?
0, r over the square root of 2 squared.
What will the top limit be?
R over the square root of 2.
No. What is it? Yeah, and you need the circle as y as a function of x.
So square root of r squared over 2 minus x squared.
Yes. Okay. What you have to do here, you're going from bottom to top. You're going from 0 till you hit the function. The function is y equals. It's a plus or minus, but we only want the top one. Square root of r squared over 2 minus x squared. Okay? That's the equation of that semicircle on the top there. Okay? Where are my x limits going?
0 to r over square root of 2.
Okay? That's exactly right. Nice job. Okay? That triple integral will give us the volume of that ice cream cone. Okay? Any questions on that?
So the first, when you're integrating in terms of z, that's the sphere and the cone solved for z,
Yes.
and then for dy, that's the sphere and the cone solved for y.
No. What the dy and the dx limits are from this region down here, from the circular region where they intersect. The x and y limits are going to be from the region in the xy plane, which is the intersection of those two surfaces.
So the y is from 0 to the intersection of the two surfaces.
The y is going from, you take their intersection, that circle, bring it down to the xy plane. Now, where is your y going to go? It's going to go from bottom, 0, to top, the function itself. Your x and y limits are determined by that region in the xy plane. Okay, not the three-space solid anymore. Because what it's doing is telling you where do we have to integrate? Where are my x's going from and where are my y's going from? Okay?
So it's the path from the y plane to the x.
Well, it's easier than that. Here's the region right here. Okay? Here's the region. Where are my y's going? The y's start at 0, constant, and they go up until you hit this function. What is this function? That function is the square root of r squared over 2 minus x squared.
So that is solved in terms of y.
Yes, y into, yes, it is. All right, okay, but it seemed to me you were doing it more complicated, but maybe you were right. You could have been right.
The last integral, is that the same thing for x where you solve for?
Well, the x one is two constants. X is going from 0 till we hit this point. And what is this point? This point right here is the point r over the square root of 2, 0. Okay?
Oh, I see.
Yeah. Yes?
Could you look at it like the reverse? I don't know why you would, but like, so like the y's go from 0 to, what was that, r over square root of 2, and then the x would be?
You could switch these two and do them in reverse.
That would be,
Yeah, you could do that.
and put it in terms of x's.
You put x here and y here, and this limit right here will be, if you're going to have the x's here in the middle, this would be y squared instead of x squared. This would still be r over the square root. The only difference would be this would be an x, that would be a y, and that would be a y here. Everything else would be the same. You could do that. Okay. I'm not sure why, like you said, but that's possible.
Usually we multiply by 4 because we're going from 0 to pi over 2, but this one was only 0 to the radius. So why do you multiply by 4?
Well, if you look down at this, guys,
Yeah.
I want to find the volume, and the volume is the 4 quadrants above the xy plane. But I'm only going to do it in one quadrant and then multiply by 4. I have perfect symmetry here. And what I'm doing is finding the volume in this quadrant here. But it extends there, and there. And you got perfect symmetry. So by finding the volume here, multiply by 4 will give me the volume of the whole thing. Okay? Because that's what we have. Yes?
If the cone extended past the origin, like into the other quadrants,
Yes, yeah.
would you multiply it by 8, or would you have to do a different integral and find the different volume?
Okay. Well, the volume would be the same because you got perfect symmetry. Now, if you wanted to consider negative volume, the volume would be 0. But generally speaking, you don't want that. What you do want is total or absolute volume, unless otherwise stated. So you would assume, if you would extend this,
No, I mean, like, if the cone was big enough to extend past the origin and still be...
Like the origin would be inside of the cone.
Yeah.
I guess we just have a different.
oh, the cone would start like down here maybe?
Yeah.
Then you got a totally different integral. You still have symmetry, but you have a different integral. You'd have to break that up into a couple pieces, it seems to me, because at this point, if you had this cone like this, you'd have to still find the intersection, but you'd have to break it up into two. Yeah, you would have a different integral.
Are we allowed to use Mathematica on the test?
No. On the test, all you have to do is set it up.
What
But
about-
that kind of a problem we're
What
not.
about Dan's answers?
What's that?
What about Dan's answers? Can we use those?
Where's Dan?
Oh man, I guess we can. He's not.
No.
Oh well.
Shoot.
Next time.
Yeah. You know what I would do with this one here? I would raise everything up a distance r. I would add r to everything. I would make the cone's equation easier. The spheres would be more difficult, but I would locate it at the origin and raise it up and do it that way. But otherwise, you're going to have to separate this into certain parts. The part above would be this part of the cone with a circle here and a circle up here. It would be a much more difficult problem. But it could be done.
Could you just move the origin if that's possible?
Yeah, that would be the same thing. Yeah. Yes.
So at the beginning, you started writing it as if it were a double integral, and it was a difference between two surfaces.
Yes.
That's all you would do for that? Are we going to
Yeah.
see it on the test? Two surfaces?
The double integral, no. The double integrals on the test are going to be for mass of a lamina, varying density,
It's the equation of the circle.
and because that was the double integral that we did. And the double integral is going to be, you're given a surface and a region in the xy plane. You're given a single surface and a region in the xy plane, and you have to write the double integral that gives the volume underneath that surface over the region. It's when you get the difference of two surfaces that you need, and a density function, that you need the triple integral.
Right, but two surfaces, you need a double integral, and you just take a different
Yeah,
one too.
yeah, exactly. So what you're going to have is one surface and a region in the xy plane. Set up the double integrals that give you that volume underneath that surface over that region. But then the double integral one I'll give you a density function. This one here, just to find the volume, you wouldn't need a triple integral.
Yeah.
You could do it with a double.
Beginning.
Yeah. Yes. Yeah. And that's what I started doing, and that was a mistake because we wanted to do a triple integral. But it could have been done with a double. Because look at, when you do the first integral, when you do the first integral, what happens? When you do this inside integral, you get the integral dz, which is z. And it's from here to here. So you plug in this for z, you plug in that for z, and take the difference. And there you go. That's the double integral.
Looking like with those endpoints?
What's that?
Double integral would end up looking like with those endpoints?
Yeah, it would be exactly what I started writing out. After one iteration of the integral, you end up with what I wrote here. Yeah. But we wanted to do a triple integral, so that's what I did. All right, so how are we doing so far?
So when you set the double integral, but you change it to a triple integral, you could essentially get the same result just by putting the constraints, like the stuff from the first integral into the double integral and just getting that.
You would have done the same thing. We get exactly the same answer. by doing as a triple, I set up an additional step, really, is what I did. Anyhow, we got rectangular. We got 2 more to go. You ready? All right, let's do cylindrical. That's the integral that you have to do. You don't want to be doing this integral, okay? Because when you do this integral and you get z and you get this, to integrate this thing here with respect to y is a pain in the neck, okay? It's a trig substitution you don't want to do, yeah.
If you didn't want to multiply by 4, would you have to do negatives for the
Yeah.
opposites of
Yeah.
the
Yes.
second integrals?
Yes.
Okay.
You don't like that 4, huh?
I just want to make sure I understand it right.
All right, you got it. You could do it without the 4 by taking,
Opposite r squared?
yeah, exactly. This would be a negative and to positive, negative to positive. That would do it.
Wow.
That would do it. But, you know,
No, that makes way more sense.
all
I
right,
just
all
want to
right, okay, you're absolutely right.
It would be each one would have to be negative to positive.
Yes,
right?
each one would. Each one of these limits of integration would be negative to positive, yes. Okay? Is everybody okay with
The
that?
first one wouldn't be negative to
This is
positive?
the first one you're going from the 2 different surfaces.
Oh, right.
Okay. Yeah, this first one here, you wouldn't have this integral here.
Sorry, Ted, I didn't mean to shake it up on you.
Nah, sorry.
It's all right. All right, how are we doing? Boy, this turns out to be a good problem. It's good.
What does the first integral do specifically?
Well, everybody's hung up on the first integral. The first integral is a double integral that would do the volume by taking the difference of the 2 surfaces. And you'd still have the same limits of integration on these 2 that you had here. If you do this triple integral and do the first integration, the inside one, integral dz, you're going to get z as that integral. And then you're going to substitute that in for z minus substitute that in for z. And guess what? You get exactly what I wrote up here as a double integral. So that's how I first started doing the problem. My first reaction was to do it that way. But we said we want a triple integral. So to do the triple integral, we needed another integral from bottom surface to top surface.
And the only difference on the test is you're going to have a kx in there for dz.
Yeah, I'm going to give you, I'm pretty sure I'm going to give you a density function in there to find the mass or something.
Can we do a problem where we find mass with rho?
We could.
3D.
All right, we could do this. With mass rho with a triple integral.
Yep.
I could do it right here. If you were to add the mass in here, let's do it. You ready? Let's do it. Tell you what, this cat finds the volume. Okay, let's find the volume. Let's add in a density function here. And the usual density functions in these are usually proportional to the distance from the xy plane. I'm just going to make it, I'm going to do it, kz. That's the usual density function that's used. So, how does that change this?
Just goes in for the integral.
Yes,
Right there.
that goes right in here, the kz. This is now the mass of this object. Okay? That's now the mass. Now I have no choice in the matter but to have a triple integral. I can't do this with a double integral now because of this density. What's that?
Quadruple integral?
There are n-dimensional integrals that are possible.
Danta.
What would that give us?
N-dimensional spaces, it's mind-boggling. You can't even imagine what's going on. It's a theoretical, abstract kind of a thing.
Just another problem Burns can't solve.
That could be it. That could be it. You may be right. You may be right. All right, you're right. All right, let's do this in cylindrical.
And that's the extent of what we're going to do with test for 7.
Yeah. Although, after that, Liam, I think your test may be a little bit different than everybody else's.
Version 2.
Yeah, version 2.
You're gonna make it.
Oh.
Yeah, that definitely won't make sense.
Oh, well. All right, let's do the same problem now. But now we're going to do it in cylindrical coordinates, okay? We're going to set this up with cylindrical. So let's see what we got. The mass is going to be still 4 times. Kz is still Kz. That doesn't change. What does change, however, is instead of dy dx, we're going to have an r dr d theta. Okay. Our limits of integration here are also going to change. This changes to what? This z, this is the bottom limit on the z's, it's going to be r. That is exactly correct, whoever said that. Did you, Adrian? Did you say that?
Yeah, it was him.
Oh, I thought so. Wow, good job. Why? Because this is z equals the square root of x squared plus y squared, and that z equals the square root of r squared, and that z equals r. The equation of that cone in cylindrical coordinates is z equals r. Okay, that's what that is.
Is the density thing, the kz, is that being integrated, or is that one of the?
That would be if you had to do the integral, you would have to integrate that. Yes.
Wait, so I'm sort of confused about how you have the d theta, the dr, the dz. Those are what you're taking with respect to, right?
Yes.
And then, so the r isn't part of that?
Yes, it is. It's part of that.
No, the r off to the left. I'm just, in the examples the other day, you put it on there.
This r here.
No, the one above it.
This r here.
Yeah.
Yeah, that's part of it, because that r is part of the r dr d theta that you need when you do that integral in cylindrical coordinates.
So the function would be r times kz,
Yes.
and then what you're taking respect to.
Yes. Yeah. Yeah. Anytime you got cylindrical coordinates, every time you have cylindrical coordinates, you're going to have whatever this function is. This could be a density. It usually is a density function. That density, but you're going to have the r as part of that dr d theta part. That has to be in there. So don't forget that. Yes.
So two questions. Is
Go ahead.
that only for density functions, or is that for like any integration?
It doesn't matter what integral you have. If you're going to go into cylindrical coordinates, you have to have an r as part of the triple integral.
Okay.
No matter what it is you're integrating.
And can you explain to me again, like how you obtain r for dz's lower limit of integration?
That I got by doing this. Looking at the lower integral here, the lower boundary here, okay, that limit right here, that is z equals the square root of x squared plus y squared. That's what it represents. X squared plus y squared is r squared, and that gives you r. No, no problem. Okay, so that's a lower boundary for
The upper boundary.
the upper boundary is the square root of.
R squared minus r squared?
You bet it is. Now this has been a source of contention here, confusion for people. This big R and little r stuff. Okay, what I'm doing now is saying that when we convert cylindrical coordinates, x squared plus y squared is equal to r squared. That is always the case. And what do you have here with this upper boundary? You have the square root of r squared, okay, minus x squared plus y squared in grouping symbols, which is the r squared. That's where this r squared is coming from. Okay. Same thing we did down here. X squared plus y squared is r squared. And that's how we ended up with the r. That's what you've got to do when you're changing from rectangular to cylindrical. Take those x squared plus y squares and replace them with r squares.
So is it harder if you start doing the cylindrical form first, or you just gotta, it's just.
That's a good question.
You wouldn't know that.
Yeah, that's a good question, because it's obvious now, but would it be obvious then? It would not be unless you were given the equation in cylindrical to begin with. Then they would give you z equals the square root of r squared minus little r squared.
Okay.
Yeah, that's a good that's a good point. Okay. Now we got the z's. Where are the r's going? From where to where?
0 to r squared of 2.
0 to r over the square root of 2. And now that's a capital R. Okay, that's that constant we have here. Now we're looking at this circle.
0 to pi over 2.
And now theta is going to go from 0 to pi over 2. Okay. Little r here is the r in cylindrical coordinates. What's that for this circle? Well, that's a constant. That's why when you have circular regions in the xy plane, you're better off, way better off, in cylindrical coordinates than you are in rectangular coordinates, okay? Because you want to use the fact that that equation of the circle is simply r equals whatever its radius is. Okay, little r is equal to that radius. So the equation of that circle is r equals big R over the square root of 2. Yes?
Yeah, so for it to be, so is pi over 2 just because it's in that quarter?
Yes, exactly. The theta limits are going from 0 here, the x-axis, up to you hit the y-axis of pi over 2. Okay. And if we didn't want to use the 4,
No, you just do pi.
we got to.
Yeah, this one's easier than the rectangular.
Yeah.
Pi math.
This integral here is not that bad. Okay, this integral is not that bad. It's pretty simple. Let's go to spherical coordinates. Okay.
Burns still has a question.
What question?
So why is the upper boundary for dr r over root 2 again?
Because that is the radius of this circle. This circle right here in the xy plane has an equation in cylindrical coordinates of little r equals big R over the square root of 2. That's the equation of that circle. 3. Let's do spherical coordinates. Now, let's see what we have now. First of all, we have a density function that's kz. We don't have a z in spherical coordinates. We need rho cosine phi. Okay? That's what z is equal to. Okay? That's what the z is equal to. Okay? That's what we did. We were doing that the other day. So that's the first thing that has to change. The next thing that has to change is this. That r that we need for dr d theta is the integrating factor for cylindrical coordinates. Spherical coordinates have a different integrating factor. That integrating factor is
Rho sine phi.
rho squared sine phi. I'm going to give you that on the test. Okay? I'm going to say put this triple integral using spherical coordinates, using the form rho squared sine phi. I'm going to give you that. Okay? I'm going to give you that. Then we have a d rho. Now, you have a choice here. You can do d phi, d theta, d phi. It doesn't really matter on the test. I might as well do it the way I give it to you on the test. D theta, d phi is what I give you on the test. Okay? Whoa. There. Okay? All right, now, I need my limits of integration. The first are row limits. Where are my row limits going from? Yes! That's it. That's why you're using spherical coordinates when you have spheres involved, is because you have an equation of a sphere that's a constant. Rho equals r, the radius of the sphere. That's the equation of the sphere in spherical coordinates. Where are my theta limits? 0 to pi over 2 still. And what are my phi limits? This is a little bit different.
0 to pi over 4.
We don't know. In this problem, we don't know. Here's the problem. The problem is we have this. All right, what we have here. Let's go back to the original. Okay. Phi is starting here at the z-axis. We need to know what that angle is. Okay, that's my ending angle for phi. Okay, so we're starting at 0, but I have to know what that angle is right there. We can do it though. This distance right here is the radius of that circle that we put down there. That's r over the square root of 2. Are you with me on that? This distance right here is equal to what?
R.
Big R is correct. Nice. So, my phi, final value for phi, if you take a look at this right triangle that we have, we've got an opposite side, and we've got a hypotenuse. We've got a hypotenuse. That's a hypotenuse.
Oh, yeah.
We got an opposite side of the hypotenuse, so we have a sine. So we have the inverse sine, phi in this thing, the sine of phi is equal to r over the square root of 2 all over r. Oh wait, who said 45 degrees? Somebody said that. It is 45 degrees here. Because what happens is the r's cancel, and we get 1 over the square root of 2. And phi is equal to inverse sine of this, which is pi over 4. Wow, that is cool. That is cool. So this is pi over 4. I think somebody said it, too. Adrian said it again. I think it was Adrian again. David said it? Oh. Omar said it? I'm not surprised, Omar. What's that?
You go back to the other page where you did the side.
Here's what I did. This is r. This is r over the square root of 2. Okay. In that right triangle, the sine of phi is the opposite over the hypotenuse. Opposite over hypotenuse. What happens here is if you multiply numerator and denominator by the square root of 2, these cancel. The r's will cancel. You get 1 over the square root of 2. And 1 over the square root of 2. That's the sine of the angle. The angle then is the inverse sine of 1 over the square root of 2, which is pi over 4. So that lower limit, that upper limit there rather, is pi over 4. Yes, Liam?
Are we going to have anything with two surfaces on the test, though?
I don't know quite. Oh, wait, I do know. Wait a second.
We just have to set this up, right?
You just have to set it up.
But even when we're setting up, it's just going to be a spherical density,
You know,
right?
there's no two surfaces. You're going to be insulted by this test because there's only a single surface and it's
It's just a density function.
and
Wait,
yeah, it is a density function, but it's very simple.
do we have to do this on the test then? Or?
Nothing like this. You're going to be insulted, Teddy, like I said. Okay. I will give you a surface, a single surface.
I won't even study then. Let's take it right now.
All right.
You want something like Tokyo's.
What?
You want something like Tokyo's.
Yeah, that's exactly what I want. Burns, I want you to like just make up a test with words that I've never even heard of. not even problems that I haven't tried, but like concepts that I've just never heard of.
Teddy, this is bad.
Just unleash your dormant anger.
What is that?
It was like the most ridiculous test ever.
You're done with it?
I know you have the capability to do so.
Oh, and
Let's see it.
Burns, make sure you boast about how much you know.
Oh yeah, that's a key concept too. Like, yeah, you gotta
Yeah.
boast. Like, you gotta show
Yeah.
like what you're doing.
You
Yeah,
have to
ask
like.
us things you haven't taught us yet and laugh at us when we can't answer.
That's how you.
You should like write in parentheses.
Now you got it. Now you got it.
After every question, Burns, you should put in parentheses. This would be really easy for me.
You have to brag about how much Latin you took in history, how you took 9 years of it, so you know what all the letters and the stuff means.
All right. Any other questions?
What were your favorite class that you've had in a while?
You guys are right. I love this class. All right. Any other questions at all? Omar!
So to calculate the moment at
That's a no.
any like axis, you just multiply that mass by whatever's not.
Yes, whatever is not. If you need the moment that solid generates about the xy plane, you multiply it by a z in there. Okay? But the z goes inside the integral. It has to be integrated. You can't just take it outside. So if you need the moment from the yz plane, okay, yz plane, multiply by x. And if you need the other moment, okay, of the xz plane, multiply by y. Yeah.
And then a step back from that, we have the density of the lambda. You have the function of the lambda, the double integral, and then for the moment from x, you just multiply by y, and the moment from y, you just multiply by x with the density function instead of the z function.
That is correct. That's exactly right.
Wow, that was easy.
You guys are too much. I was laughing. Hey, anything else?
Was that you didn't do the X bar, Y bar? You don't need that for this.
For this, I asked you how you would find the X bar, or Y bar, or Z bar. No, I don't for this.
Does that just mean the definition?
I do ask for an X bar in another problem in the other section. So you have to know how to find X bar.
That'll be in 2.
And how do you find X bar?
What actually is X bar?
Oh, that's
X bar is the distance from X.
X bar would be the moment from the YZ plane divided by the mass. That's the answer I'm looking for if it's X bar. Y bar would be the moment from the XZ plane over the mass. What these are the X, Y, and Z coordinates of your center of mass. That's what X bar, Y bar, and Z bar are. The center of mass, the coordinates for those. So I'll ask you one of those, and this is all what you have to know is what this.
Are we gonna have to? So we won't even have to find X bar, Y bar, and
No.
Z bar for any.
No.
But we will have to find X bar and Y bar in the section before that with the limit.
No, I don't ask. I don't think so. No, I don't ask for that.
I thought like number 6 through 10.
6 through 10, you have to find the moments. That's the lambda question.
Oh,
Now we're in 3 space. In 3 space, I'm going to ask to set up the triple integral that gives you the moment from the XY plane. This is Omar's question. We have to put a Z in there with the density function. And I'll ask you how to set up the triple integral that will give you those moments.
So you set up the Z with the density function, and then you put in for your limits of integration Z, Y, X, dz, dy, dx.
Yes, yes.
It's the same as the density function, just multiplied by Z.
Say that again.
It would be the same as like a density function. I mean,
I know, I need it.
All right. Say it one more time, Omar. Sorry.
it's the same as like the triple integral.
Haven't had one yet this
when you're solving for
semester.
density.
I'm just hungry for it.
The X bar?
Yeah.
X bar. What you would do for X bar is find M of YZ, and you would find M of YZ by taking the density function times X.
So you take like KZ and multiply by X?
Yes.
Okay.
Yes. Any others?
So it would be the same integral for...
Yes.
Okay.
The order of which they.
Anything else? Okay. See you tomorrow. All right.
Mr. Burns?
Yes. You could remind me, and I'll put it in the.
Yeah.
What's that? I'll put it in the morning. You can take it whatever. The test is tomorrow, right? Yes.
So I have that printout thing.
It's just the same.
Formulas.
Trig formulas?
Can I bring that in?
Yeah.
And can you put a note on the exam just saying I have that because they're kind of upset about that the last time.
They got upset?
They didn't really get upset, but they said like.
I should put it on the exam?
Yeah.
Just remind me in the morning, all right? I can do it.
Burns, let's do this. Don't turn that off. We're probably late.
I'm going to turn the recording.